All right, good morning, everybody. Before we get started thinking about the CPU, any general questions about the memory concepts we went over in the last two class periods, or any conceptual issues with building your RAMs? Okay, so without further ado, then we're going to start thinking about how we would write machine language programs given this architecture. So we go over some basic ideas about machine versus assembly language in general, how they're realized in different CPUs, and then we're going to look into the specifics of the machine we'll be programming as described in chapter 4. So first is machine versus assembly language. So what's the distinction here? These terms often get used in interchangeable ways. And so because of that interchangeability, there can be a lot of confusion about what precisely is meant when they're thrown around. So I'm going to start by talking about what precisely is meant, and then I'm going to talk a bit about why the terms tend to get thrown around together a lot. So strictly speaking, when we're talking about machine language, what we're talking about is machine instructions expressed as numbers. So thinking about the idea of a machine instruction expressed by a number more readily enables us to relate the idea of a machine instruction back to the idea of a circuit, which we've been exploring in a lot of detail. If every machine instruction can ultimately be represented as a number, numbers in turn can ultimately be represented in binary. And once we've got binary, we have a circuit input, or more precisely, a digital circuit input. And so that's what we achieve by having this numerical representation. So that relationship back to the circuitry becomes clear. The disadvantage of thinking in terms of numerical machine instructions is that for the most part, they are largely incomprehensible. That is, you can stare at it and you can pick it apart and you can figure out what it means through application of a sufficient amount of mental effort. That's a lot of work. And in terms of just trying to sit and read the code, they're basically incomprehensible. And there's no shame in admitting that. Okay. So very, very early in the history of digital computing, people came up with the idea of an assembly language. So the idea of an assembly language is that machine instructions are expressed as symbols. So, in other words, instead of having some numerical representation of what the instruction is, we actually come up with a symbolic representation that's fundamentally easier to read for a human. Now, this has its own advantages and disadvantages. What's the biggest disadvantage? The biggest disadvantage is that this must be translated, right? So we've got this symbolic representation, and it's more readable, but at some point we need a computer program to turn it into bits. Of course, one might wonder, what about the very first translator? Did they just write it in raw machine language and then enjoy its fruits? Well, what likely happened was they actually specified the assembly language and then translated it by hand. And after translating it by hand, they could now take that same assembly language program and translate it automatically. Curiously, this is also how most compilers are written. That is, most languages have a compiler that's written in themselves. And a lot of the beauty of that is it enables the compiler to be its own best test case. If it can compile itself, you've got some confidence that the language is doing what you wanted. Yeah, I am not remotely kidding about this, actually. Yeah, Innocent.
I have a question that's probably not answered a little bit. I've been asking myself about this question for long, but this might be the best.
Go for it.
Environment.
Yeah.
You know how we have text editors?
Yes.
And we write programs from them?
Yeah.
To create softwares?
Right.
And I believe that text itself was programmed through another text editor, right?
Right. At some point, it had to bottom out.
Yeah. So somewhere from the root.
Yeah.
Like the first text editor, how was it programmed? You see what I'm saying?
I do.
Uh-huh.
It would have been programmed in machine language.
And then whoever programmed the machine language, what did he use? Because there's shade.
Oh, okay. So early computers had switches. Mm-hmm. So what you could do to enter an instruction was you would flip the switches to correspond to each bit in the instruction. And then you would hit a button to enter it into the program memory. And then you would flip the switches again. Actually, a Turing machine is even lower level than that. Like that's a very high level of abstraction compared to a Turing machine. Well, we'll talk about that probably on Thursday this week, actually. So I knew in principle that these things existed. These machines with the switches and you hit the button. So I was in high school at the time. And there was an exhibit about the early history of computing at the local science museum. And I thought, well, that looks interesting. And so my father and I went. And just to give a bit of background, my father got a degree in electrical engineering in 1969. His first job was to work for IBM in South Florida. So my father actually took a programming class for one semester in college. He hated it. He swore he was never going to program again. And at his first job with IBM, you can guess what he did. Yeah. In the end, my dad actually taught me a lot of programming. But in any event, we're at this museum exhibit, and they have one of these machines with the 8 switches and the button to enter the instruction. And I made some comment about, it was interesting to see this. You know, I would never have expected to see it outside of a museum. I can't imagine having to use this thing. And my dad looks at me kind of sheepishly and says, I had to program using one of those. So, you know, yeah, at some, so the real issue actually, Innocent, comes down to this. People got stuff working with those machines, and it took them a lot more time to get an equivalent program running than it does now with all of our text editors and everything. You know, you can do it. It's just really painful, as you all will be experiencing this week, as you write assembly language programs. I mean, it's not going to be quite that painful, but it's not going to feel good. I mean, in some ways it will, but in others not so much. So the big con is this stuff has to be translated, and that translator is known as an assembler. And so it's called an assembly language because an assembler assembles it into machine language. But assembly language has an enormous pro, which is a one-to-one mapping from ASM to machine language instructions. That is, if you write a program, whoops, I shrank that a little too much. If you write a program in assembly language, that's the exact same program you would have written in machine language. There's nothing between what you wrote as a program and what the machine is going to do. Now, any program you write in any higher level language, Java, Python, or whatever, ultimately is translated into a machine language program. That's the only way they can work, right? Like, there's no fundamental physical realization of a Python program. There doesn't exist a CPU that can take as input the text of a Python program and do what it says. No such CPU exists. So what happens is that Python program is ultimately translated down to these ones and zeros. In that process, the translator, not being as fully cognizant of your will or your intent as you are, could introduce an awful lot of artifacts or a lot of unnecessary instructions relative to the goal of your program. And so there's a sense in which if you can write a program in assembly language, in principle, it's going to have the potential to be maximally efficient compared to a program in a high-level language. Now, of course, people know this, and so compiler developers for high-level languages go through enormous amounts of effort to create what are called optimizers. That is, special compiler passes to transform the code it generates to get rid of a lot of these artifacts and the like. For the most part, a really good optimizer running on code from the right kind of high-level language can generate very, very good code. But it depends a lot on what transformations the language facilitates. So in practice, the high-level language that tends to facilitate the most efficient assembly code is Fortran. So Fortran was a language created again in the 1950s because the first electronic digital computers came online in 1945. By 1954, people were sick of assembly language. It didn't take long, as again, you will be experiencing. Fortran was developed to enable programmers to write out arithmetic expressions in an algebraic way. And for a lot of reasons, Fortran remains the language for which it's easiest for a compiler to generate highly efficient code. But there are others as well. Java actually gets remarkably close in some ways, although it has some gratuitous problems as well. Python, it's really hard to actually make the code efficient. And that has to do with some highly technical reasons about its type system. And if time permits, we may get into some of that later in the semester. Yes?
So, as you're mentioning that most of the complexity and time consumption of comparing a program comes from translating from a high level to a lower level,
yep.
A machine can understand.
Yep.
Is it possible to perhaps, like, as writing a program, to compare it in real time immediately? So that, like, let's say, public static, maybe like an array list or something, and then instantly the compiler creates like
the assembly code.
Yeah, assembly code. So that when I finish my program and I click run, it doesn't take what I'm writing, but take what was translated, so that the compression can be much faster. Is that like
It is technically possible. It doesn't tend to be done in practice, in part because of optimization passes. That is, certain kinds of optimizations require the compiler to take another pass through the entire generated assembly code to kind of clean things up. Essentially, the effort winds up not being proportionate to the payoff. Yeah. One thing that we're going to learn as we develop a compiler this semester is the seemingly absurd number of assembly language instructions that corresponds to a single high-level instruction. So you start typing while or whatever, and you just start seeing this avalanche of assembly code appear on the right. And that's kind of why, in principle, nobody's terribly interested in doing this. That makes sense. Cool. Other questions thus far? All right, so I've talked a lot about the principle and the concept. It's time to get into some details. So in other words, what are the typical abstractions available to a machine language programmer? And now I'm actually going to start using the terms a little interchangeably. And the reason the terms are used interchangeably ultimately comes back to this one-to-one mapping. That is, if I am writing a program in assembly language, there's no abstraction barrier between that and machine language because everything is at a one-to-one mapping. So I can talk about, well, I've created a machine language program even if I'm writing out assembly language instructions, because fundamentally they're going to turn into the same thing. So that explains a lot of how these terms tend to get mixed up. But if one is being highly precise, this is the distinction between the terms, and it's good to be clear on that distinction. Okay, so what are the main abstractions available to an assembly language programmer? And this applies essentially to any assembly language, not just what we're going to be specifically looking at, but basically any assembly language. So the main abstractions are going to be load a value from RAM onto a CPU register, store a value from a CPU register into RAM. So this is huge. This is like an enormous amount of what an assembly language program does. It's just move values from RAM onto the CPU. And when I say onto the CPU, what I mean is the CPU has its own registers, which are the main places where it does computation. A really basic CPU might have as few as 3 registers. So many modern CPUs have as many as 64 registers right there on the CPU. So you can guess what we're going to be doing. We're in the 3-register territory. But a lot of kind of hardcore modern CPUs with 64 registers or whatever will actually have compiler optimizations that do things like try to cram all local variables and parameters onto CPU registers. The motivation being then you don't have to go to RAM as often if they're just right there on the register. Okay. So adding, subtracting, and or. So kind of basic mathematical operations. There are some CPUs that will go a little more advanced. There exist CPUs that have multiplication built in. For example, the disadvantage of having multiplication on board the CPU is the complexity of the CPU circuit itself skyrockets once you try to do something like multiplying. It's not impossible, but it's kind of nasty. But in general, kind of arithmetic operations. In other words, ALU kinds of things, okay? And then, very, very importantly, jumps. So a jump is some kind of a change in the control flow of the program. So normally the program kind of marches along sequentially through memory, grabbing one instruction at a time. A jump says, forget that, go to this place over here. Very, very important aspect of jumps is that you can also make them conditional. That is an essential operation for a CPU to provide is to say, I want to make this jump, but only if some condition is true. Now you might be wondering, where do the conditions come from? And the answer is the ALU. Where in the ALU do you all think those conditions come from on our machine? Remember anything about the ALU outputs that might feed into jump conditions? NG and ZR. Yeah, that's right. So what were NG and ZR?
ZR told you if it was 0. ENG told you if it was negative.
So let's say you wanted to jump on something positive. Could we take those two wires together easily and say, I want to jump on a positive? How would I do that? So I've got a 0 detector and I've got a negative detector. I'm suggesting we need to create a positive detector from those two. What kind of gate might I use to do that? Or how might I build a circuit that does that? Yeah, Andrew.
We just test like a circuit that checks not both of them and together.
Exactly. So you put a NOT gate on each of those, right? So you've got NOT 0, you've got NOT negative, then you have an AND gate. So if it's NOT 0 and NOT negative, it's positive. So there it is, right? Yeah. So yeah, conditions on jumps are very, very important. There is, without the idea of a conditional jump, we would not be able to call it a proper CPU. Really, any CPU is going to need all of these things. Okay? Some way to move from RAM onto the CPU, some way to move from the CPU to RAM, some form of arithmetic, and some form of conditional jump. Every CPU has to have instructions to do this. But once you've got this, there are lots of different ways you can realize this. So you can wind up looking at assembly languages for two different CPUs, and they can look totally different from each other. They might be set up in all kinds of different and strange ways. But if you drill deep down, they're all doing this. Some of them are more elaborate, especially at the ALU level. Some of them have much more sophisticated ALUs that can do a lot more calculations. There are modern CPUs at this point, and this is very common, that have what are called floating point coprocessors. That is kind of a side chip that does arbitrary floating point calculations, and you can express them all in machine language. So if you need a sine or a cosine, you ask the floating point coprocessor. And it's got circuitry that calculates all that stuff. We're not doing all that in this course. It's certainly doable, and it's done frequently. To call it a large amount of work is a bit of an understatement, however. But this is the essence. This is what we need to call something a CPU. Okay. Questions so far?
So question.
Yeah.
So are these things like exhaustive? And there are some other really powerful CPUs that can even do way more than this, times 2 times 3. This kind of operation.
It really kind of comes back to elaborations on the ALU, variations on the idea of a jump. So, for instance, you can imagine a jump where you say you go to exactly this memory location, Or you can imagine a jump where you say, go 20 bytes ahead of where I am, which is called a branch. Then there are issues with, is the RAM the real RAM or kind of a fake RAM? So there are huge numbers of issues with that kind of thing, which I go into in a lot of detail in my operating systems class. But in effect, the fundamental issue is that RAM accesses are slow in general. And so many modern CPUs have their own special bank of RAM on board the CPU called a cache. And so then there wind up being operations that depend on goofy things happening with the cache. On a related level, some CPUs are sufficiently clever that they'll do things like, if you run out of RAM, start automatically storing stuff on your hard drive. And it's all transparent to the machine language program. But it provides instructions to configure stuff like that. Like, how do you map what are called virtual addresses, that is this make-believe infinite amount of RAM, onto physical addresses in memory and sectors on the hard disk. So there's a lot of stuff like that that makes its way into a modern CPU. So yeah, they do have a lot of neat tricks, but the fundamentals of what they do are these. So if you look at something like this, and I'm telling you, this is everything a program does, because if I say this is the abstractions presented in a machine language, that means this is everything a program can do. Then we're faced with interesting questions like I/O. And the answer is I/O can be implemented by making it look like RAM. That is, I can store a value in a certain memory location, but if the CPU's address bus is wired so that data from that location actually goes to a chip that puts stuff on the LCD display, then it's all the same to the program. You know, the machine language program is just sort of mindlessly moving data around. And I mean it. It's mindless, and it's moving data around. But the result, based on wiring a screen to it, is suddenly moving data around becomes cool pictures or text or what have you. Similarly, we can read data, and that means there's nothing stopping us from wiring a keyboard to a region of the CPU's address bus. And now there's a certain memory location I can read that tells me in binary, here's the key that was pressed. Well, if you've got a way to change the pixels on the screen by storing in memory, and you've got a way of reading what the keyboard is saying by loading from memory, suddenly we're in business. Same, of course, applies to a mouse. Actually, it even applies to a network card. In the end, the network card is just mapped to a region of the CPU's memory. By being wired to the address bus, we get everything we need. When I say wired to the address bus, what do I mean? The CPU is soldered onto the motherboard, right? And then where it's soldered onto the motherboard, there are wires going out to peripheral ports. You then plug in a peripheral to the port, and in effect, it's now been wired to that section of the address bus of the CPU. And like, that's literally how everything works. Let's say I want a robot. You all know I like robots. Well, I store a value in RAM, which is wired to a motor that's connected to the CPU via the address bus. I read a value from a sensor. What does that mean? The sensor is plugged in to some part of my motherboard, which is then wired to a region of my address bus, and I can see in RAM what the sonar is saying. So what I'm hoping you all are grasping from this is, given these instructions, you can write a program that does anything a computer does. Yes?
I got a question.
Yeah.
Kind of in this.
Yeah.
I've heard of these computers called quantum computers. yeah, this sort of does like some magic stuff. Like,
Right.
I wonder, like, are their CPUs also in the same leagues as these ones, or they're sort of different?
A quantum computer is not doing anything fundamentally different than this. The distinction with a quantum computer is actually, the quantum part is in the ALU. So in principle, a quantum computer can perform arithmetic operations with a greater degree of parallelism than a conventional CPU. A quantum computer, however, at this stage cannot be considered to be anything other than a research project. Like, you are not going to be able to buy a quantum computer in the marketplace anytime soon. There's still a lot of basic research that needs to happen before they become usable products. So there are some prototype quantum computers that do really cool things with essentially toy problems, but they have not truly been scaled up to be usable. If they were, however, it's all about just having an ALU with higher throughput. That's what it gives you. So, great question. All right, so we've gone from talking about, in principle, machine language and assembly language, and we've talked about what kinds of operations are available in a machine language or an assembly language. So what we're going to do now is start examining what about the machine language in which we will be programming, as described in chapter 4 of the textbook. So that's what I'm going to go over next. So, in thinking about this machine language, which they're calling hack machine language, so they have named their CPU the hack, and then ultimately the high-level language we create, they're going to call Jack. So anyway, so hack machine language. Each instruction is 16 bits, 16 binary digits. And there are two fundamental types of instruction on the CPU. Why are there two fundamental types? They relate directly to the two primary registers in the hack architecture. Those two primary registers are known as A and D. A is what's called the address register. And as we'll see, A is the primary means by which we indicate what memory location we want to perform an operation on when we're interacting with RAM. A is kind of multi-purpose, though. You can also use it for the same purposes that we use D. D is called the data register. And the idea of D is that if you've got some piece of data that you just need to hang on to on board the CPU for a very short period of time, there is no long-term storage in D. Okay. But if there's some data that you want to do something with, you typically put it in D, and then you do whatever you're going to do. So, given all of that, let's examine what do the 16 bits in an instruction actually mean. Now, by convention, when we talk about the bits in memory, we number them from 0 to 15, okay? And because of place value, bit 15 is the one that's all the way on the left. Bit 0 is all the way on the right. Bit 15 is known as the most significant bit, or MSB. And then bit 0 is known as the least significant bit, or LSB. So when I talk about the most or least significant bits, when I say most or more, I'm going left and upward. If I say less or least, I'm going right or backward. So I could talk about the three most significant bits. If I say that, I mean bits 15, 14, and 13. If I say the three least significant bits, I mean bits 2, 1, and 0. And I'm going to throw around vocabulary like that all the time. So I'm just warning you now. But don't hesitate to interrupt if you're confused. Okay.
That's a good question.
Yeah.
So if I write the bit string,
Yeah.
then the most significant are like on this.
On the left. Yep.
The numbering is sort of reversed in a way.
Well, it corresponds to our conventions of place value. So if I have the number 123, the most significant value, the 1, is on the left. That's my hundreds place. And then the 3 is the least significant value. That's on the right in the ones place.
Okay.
So our convention for binary numbers follows that convention. So if you just think of it as a number and think about how our intuitions for laying out digits mathematically, I think you'll find this to be intuitive. But yes, it's important to warn you ahead of time. All right, cool. So having said all of that, there are two types of primary machine language instructions in the hack architecture, and they depend on that most significant bit. Let's say the most significant bit is a 0. That is what is called an A instruction. So what do we mean by an A instruction? An A instruction means take the lower 15 bits and those go immediately into the A register. So if you start with a 0, the lower 15 bits all immediately are placed in the A register. So this is actually the only way you can load a constant onto the CPU other than a 0 or a 1. So if you've got a constant you want to load, you have to use an A instruction. Typically those constants are addresses, but other kinds of constants can be loaded this way as well. So that's an A instruction. In assembly language, this is denoted with an @ sign and a value. If you write an assembly language program, it's @ value. That means take the value, stuff it in the A register. So in general, what you're going to find is that your programs alternate between these A instructions and the other kind of instruction, which we got when the most significant bit is a 1. And this is called a C instruction. You can think of A as address and C as calculation or computation. So what about a C instruction? Well, C instructions are going to be quite a bit more complicated. But they're pretty easy to understand if you think about the different regions of the 16 bits and what those regions mean. So let me go over those with you. So we've got 16 bits overall. So we've got 3 bits here. That's 15 to 13. These are all 1s all the time. So bits 15, 14, and 13 are just 1s. They have no deeper meaning than that. Next is bit 12. This bit is known as A. What does that mean? A indicates whether the address denoted by the A register is itself an ALU input, or if the memory contained at that address is an ALU input. So when A is equal to 0, the A register is treated just like the D register. It's just data that you can ALU on. When A is 1, it means do a memory lookup from RAM and use the A register to find some location in RAM and now bring that value in. The next 6 bits, so this is starting at bit 11, 10, 9, 8, 7, 6. These are called the C bits. And so these are C1, C2, C3, C4, C5, dang it, C6. These bits go directly to the ALU. So these are the ALU bits. These control what calculation is performed. Next, so we have bits 5, 4, and 3. And these are called D1, D2, and D3. These are known as destination bits. So in other words, stuff comes into the ALU from the A register and the D register. Sometimes, instead of coming from the A register, it actually comes from RAM, denoted by the address in the A register. ALU things happen. Then that stuff's got to go somewhere. And so these bits control where does it land? Where does it wind up? And so there are 3 possible landing sites for data: the A register, the D register, and RAM. And so one of these will be for the A register, one will be for the D, and one's for RAM. Off the top of my head, I don't remember, but we'll look it up when we need it. Finally, we've only got 3 bits left. 2, 1, and 0. These are the jump bits. So each jump bit corresponds to whether a jump is happening given a certain condition. So again, I don't remember which is which. We can easily look it up. But the concept is this. One of these is ALU produced a result that was positive. One of these is the ALU produced a 0. And the final one is the ALU produced a negative value. And so if that condition is true and the jump bit is set to a 1, then the CPU will jump to the address in the A register at that point. And at this point, we have seen the entire machine language for this CPU. This is literally everything it does. And what I want you to notice is how I have fulfilled the promise given up here. Thanks to our destination bits, we can load a value from RAM onto the CPU or store a value from the CPU into RAM. To be fair, I kind of glossed over something here, which is you can move values between registers as well. Add, subtract, and or, it's the ALU, and you can jump, and the jumps can be conditional. Now, there are a lot of fun kind of emergent properties from this that enable you to do some desirable things. For instance, let's say you want an unconditional jump. Well, you set all 3 of these to 1. That way, it jumps if it's positive, if it's negative, or if it's 0. So it just became unconditional because we just said it jumps on all the conditions. What if you want an instruction that doesn't jump? You set all of these to 0. What if you don't want to change the data register, A register, or RAM? No problem, you set all these to 0. Now, how often does that happen? It basically happens when you jump. So typically on a jump, you're going to want to do some kind of an ALU instruction and specify where it's coming from. And then depending on the outcome, you jump, but you don't actually want to change anything. For example. Similarly, if you're doing a complicated arithmetic calculation or complicated by machine language standards, like you're adding or subtracting, you typically don't want to jump on the same instruction. And the reason for that is our A register is a very busy B, right? If you're doing a calculation, then that means you're either accessing the A register or you're accessing RAM. Well, if the A register is also telling you your jump destination, well, you don't want to munge them all together. That would be kind of a mess. So you're not typically going to be trying to use all of these in one instruction. Okay. So that's everything that the CPU can do right there. Bam. What does this look like as assembly language? Okay. So as assembly language, what we do is first we're going to focus on ALU calculations. Let's say you've got a calculation you want to perform with a given destination. The destination will go on the left, like D, for example. And to specify that it's a destination, you then use the equal sign to say, I'm changing this. On the right, you put the calculation that you want the ALU to perform. For example, let's say I want the value in my data register to be the sum of itself and a value in RAM. I can say D equals D plus M. Now let's say I just want the value from RAM. Well, I can say D equals M. What if I want to increment D? I can say D equals D plus 1. Now, you might be wondering, what's the scope of possible expressions on the right-hand side? And the answer is precisely the operations supported by the ALU that you constructed. In other words, I am not allowed to do this. Why not? Because plus 3 is not an ALU operation. But plus 1 is. And it all comes back to the bits. That is, every assembly language instruction corresponds to a specific 16-bit value. Any ALU calculation has to be expressible with the 6 ALU bits. So you can do anything that those 6 bits let you do, and literally nothing else. Yes?
Can I perform a loop there so that maybe on each iteration I add one?
Oh, certainly. The question is, how do we do it, given these basic operations? So what do you all think? If I want to build a loop, what kinds of operations do I need to do, given that these A and C instructions comprise my entire working vocabulary? And now he wants to build a loop. Savvy, what were you going to say? It was just a gesture of, well, you would do something. You know, if you prefer, think in these terms. I'm writing a loop in a machine language. That's my vocabulary. What would it look like, abstractly speaking? Yes?
Maybe I would like load the value from around, store it in a variable, and then do something like do this until this variable have is got the value that I loaded, and then sort of do something, go back to the RAM, load another value, come back, do something, go back to the RAM, load another value, and if that value is got to the value that I set up, and sort of send it somewhere into a memory.
You're getting there.
I was essentially thinking, load something in, create it and store it, perform your operation, store that information, jump back to the top, continue going over and over.
So Savvy's got the key idea right there, which is you load values onto the CPU, you perform calculations, and then you do a test. And if the test is true, you jump back to the start of the loop. And then you keep going, but eventually the test is false, the jump fails, and then you fall through to the next instruction. I mean, so that's a while loop in a nutshell. Now, as it happens, a while loop is a lot prettier than doing this. And it's a lot prettier on a number of levels, okay? Jumping, while essential in machine language, is actually kind of an ugly operation, by which I mean it leads to what is commonly called spaghetti code. That is, code with jumps tends to be intermingled like a giant bowl of spaghetti. It can be really hard to reason about where control flow is going in the program. Obviously, many of our high-level constructs are simply cleaned up jumps, right? If is a cleaned up jump. While is a cleaned up jump. Function calls are cleaned up jumps. Function calls are especially fun because they jump back. Return is just a jump to where you came from. There's really nothing to it beyond that. Well, there is something to it beyond that, which is, how does it know where it came from? Any guesses? How would a return know where it came from? What kind of a data structure would we use? Thinking back to data structures. You'd use a stack. Every time you call a function, you push everything about what you're currently doing on the stack as you wait for the function to return. Why? Because when you call the function, that's the behavior we're used to. You call a function, it comes back, and it's like nothing changed except I got a value back from the function. Well, then what if the function calls a function? Well, then it needs to just kind of pause, right? Last in, first out, stack. Whoa. Yeah.
Can you store a function on a stack? Because a function is not even a variable. Like it's literally.
By the end of this semester, you will have stored a function on the stack. Oh, yes. As you'll learn, the program stack is actually where functions live. You don't just have to store a function on the stack. Everything about the function goes on the stack by default. The stack is its home. And it's going to make life a lot simpler once we get there. But ultimately, it's just these disguised jumps. Now, what are these disguises doing? They're automating a lot of common tasks. You know, if you didn't have functions, it would be a ridiculous amount of work to save everything you're doing, jump somewhere, let it do some stuff, and come back, and then you've got to undo all of that, right? It's nice to have functions. Similarly with a while loop. Sure, you could just sort of code it as a jump and all of that, but the while idea, you look at it and it's like, here's a block. Do the block as long as this is true. Bam. Same thing with an if. Do this block if this is true. Do this else block if this is false. It's a lot more straightforward. But ultimately, it's just this. All right, cool. So what if you want to know a comprehensive list of these things? You want to look at page 67 of your textbook. And page 67 of your textbook has a comprehensive ALU chart with the appropriate assembly language instructions. Okay, so that's the ALU. Actually, it's both the ALU and the destination. So on the left, you can have D, M, or A. D is the data register, A is the address register, M is RAM, where the RAM location to be updated is simply the address given in the A register. Okay? And then what about jumps? Well, you put a semicolon, and then you've got one of several formulas. They all begin with J. So JGT, for example, is you jump on a positive number. JLT would be jump on a negative. And then there's other combinations as well. So JGE is greater than or equal to 0. JLE would be less than or equal to 0. JEQ is when it's equal to 0. This one is fun. JNE is when it's less than or greater than 0. In other words, not equal to 0. But fundamentally, what is not equal to 0? It means negative or positive. Interesting. And then we have JMP, which is all of the above. In other words, JMP is an unconditional jump. And that's it. That's like totally everything. And you're like, no, that's not it. And I'm like, yeah, actually it kind of is. But it's a little more meaningful to see this as a program, right? So here's what I'm going to do. I am going to start up the CPU emulator. So the CPU emulator on Windows.bat on Mac.sh. Okay. So this is kind of neat. It gives you the CPU as a visualizable whole. It also has a simulated keyboard and a simulated monitor right here. Okay. So this is the ROM, the read-only memory. This is where your program goes. This is RAM. This is stuff the program is doing. Over here, we have the onboard CPU stuff. So you've got your D register, and then your A register is down here. I mentioned there were 3 registers. The third register is the program counter over here. Okay. Program counter, address register, data register. Then over here is the ALU. So the ALU has 2 inputs, the data register, and then a choice between a value from RAM or the A register. Any guesses off the tops of your heads what kind of circuitry you're going to need to determine which of those 2 goes into the ALU? A multiplexer, yeah. Like, when it comes to next week and it comes to designing your CPUs, if you just think, when in doubt, multiplexer, you'll be in good shape. You know, whenever you're confused, whenever you're befuddled, just to think, multiplexer. And then you'll be like, okay, well, that makes sense now. It'll be literally everything, much like developing the ALU itself was. Or, you know, sort of a festival of multiplexers, right? Same thing's going to happen here. Okay. So I've put together a short little program to show how all this stuff works. Okay, this is ridiculously tiny. Okay, this doesn't seem to have a nice way to make the font bigger. So you know what I'm going to do? So I'm actually going to show you my source code in Notepad++. So Blake, is this readable back row? Not at all. Okay. How about that? Okay. So here is a very short and somewhat pointless assembly language program, but let's walk through it and get a feel for how it works. So you'll notice alternating A and C instructions. This is going to be a very common pattern in the machine language programs that you write. So at 50, D equals A. So let's just stop right there. What do you all think the CPU is going to look like after that executes? By what the CPU, I mean the registers. Yeah.
A and D will have the value 50.
Exactly. Okay. X, M equals D. Okay, now this is weird. Where did X come from? X is what's called a label. Labels are very important in assembly language programs. What does a label do? What does it mean? How is it defined? Where did it come from? Or it came from, of course, is that I made it up. But what did the assembler do to it to map it to machine language? So what our assembler does with labels is two things. The first thing it does is, let's say it has no other basis for knowing the value of the label. It's simply going to assign arbitrary values to them according to the following scheme. The first undefined label it sees gets the value 16. The second one it sees gets 17. The third one it sees is the first was 16 and the second was 17, 18.
Oh, okay.
And then the fourth one would be 19, yeah, and the fifth would be, exactly, yeah. So what's going on with this? What's going on with this is that memory locations 0 through 15 have reserved uses. You know, they have purposes. Starting at 16 is where, from the assembler's point of view, we have free RAM, unclaimed, without a purpose. So every time I introduce a new label, it just puts it at the lowest available location in free RAM. And then from here on out, that label corresponds to that address. So what I've done here, in effect, is I've declared a variable. Now, what does declare a variable really mean? It means I gave a name to this memory location, and now I'm going to do things to it. There's really nothing more to a variable than that. It's just in machine language, it's very transparent. Like, it's literally nothing more than that. Okay. So I'm saying memory location 16, M equals D. So I want the value from D to go to that memory location. Now I have at 4. What's that going to do? A is now equal to 4. D equals A. And then at X, and now M equals D plus M.
So at X means the reading value from the memory location 16.
That's right. Mm-hmm.
And then I take value from the memory, which is at the moment is equal to 4.
Yeah.
Plus D value, which is also equal to.
Oh, no. M is this.
M was view.
Yeah.
Okay.
Yeah. This 4 lines of code was basically X equals 50 in a high level language.
Okay. Oh, that's 50 plus 4.
Yeah.
Yeah.
So let's try it out. So here's my program. And what I'm going to do is I'm going to walk through it one instruction at a time. And what I want you all to see is that as you process each instruction of the program, the simulator is going to illustrate the state of the CPU. So this is really, really important, both for understanding what the programs are doing and, God help us all, debugging them. All right, so I say at 50. Now, A is 50, and my program counter advances to 1. And that line 1 is highlighted in yellow. D equals A. So now A is 50 and D is 50. Also very interesting, my ALU has an MA input of 50 and an ALU output of 50. So in other words, my ALU bits got set so that it just output the Y value. You all might remember when developing your ALU, right, you could pass through either the X or the Y value as the output. And the way that you implemented that, right, was you basically did an AND with all ones on the other input. So that's what it just did right here. At bottom, it's all circuits, people. Okay, so next, at 16. So the A register is now a 16. D is still at 50. And actually, the ALU has been left alone. It's just got the values it had last time. There's nothing about this instruction that changes what the ALU is doing. Next instruction is M equals D. So what's that going to look like? D came in as a 50, right? Because that's what was stored there. The MA input actually came in as a 16. Why? Because it's what I set the address register to. Now, M equals D means the only output I'm going to get from the ALU is just the X input, 50. So this A register value is being ignored by the ALU. The 50 passes through. And now the destination, M, changes the value at location 16 to 50, which is highlighted right here in the simulator. So next I have D equals, or I have at 4. And so the only thing that changes is my A register is now a 4. D equals A. So my MA input is a 4. My D input is still a 50. But it doesn't matter because all I want out of the ALU is the A value. In other words, the Y input. And I store that in D. At 16, my address register is now 16. And now the final instruction in this program, M equals D plus M. So what happens here? D is 4, M is 50, D plus M is the operation, it's 54, and it's stored back at that memory location, which is now 54. I know this is an awful lot of instructions compared to what you do in a high-level language. On the other hand, I want you to begin appreciating how at this point, even with this glimpse at machine language, you can already begin to visualize as machine language what each high-level instruction you program is doing. Questions thus far? Yeah, Innocent.
Earlier you mentioned that we do not have an ability to add anything other than 1. We can only add like 1 to something, not like 2 or 3 or 4 or 5.
Right, we have to use the A register to set another constant, which is what we did here. So if I wanted to add 4, I loaded a 4 into the A register, stored that in D, then I pointed at location 16, and now I'm able to actually add my 4.
So which other that is doing the job? Is it the other we built, the 16 other?
Oh, deep down inside your ALU is an add 16.
Okay.
Yeah, and it's doing the job. Yeah. Other questions thus far? Any other questions thus far? All right. So what we're going to do next is edit this program a little bit to try a couple other things. For starters, it's time we did a jump. So let's get a feel for what it would look like to jump. So let's see. Let's not start at 50. Let's start at 5. Store that in memory. And now, oops, didn't quite mean to be that brutal. Well, you know, I think actually we will be. All right. So I'm going to declare a label. And so the convention with labels is that you use all capital letters for them. I think actually I was supposed to surround the silly thing with parentheses. Yes, I am. Okay. Typically, labels we put on lines by themselves. Notice that introducing a label doesn't actually generate a machine language instruction. It just says, give this variable the value of the address of the next instruction. So here's what we'll do. We'll say at x m equals m minus 1. We'll subtract 1 from the value in RAM. And now what we'll do is we're going to keep doing this until it hits 0. So we will ask this memory location its value, m, jgt. Oh, no, actually, this isn't quite going to work. You're about to see a lot of the fun of the art of the jump. The issue is we can't really just directly look at M because our address register is overbooked. So here's what we're going to do. We're going to load the value from RAM into the D register. And you can do that. So you can specify multiple destinations. Now on a circuit level, this is really pretty simple, right? Each destination is its own D bit in the CPU, right? And so if each one is its own D bit, each one just represents whether a certain kind of circuit is letting a value in. What kind of a circuit might that be? Well, ultimately there are D flip-flops behind it. But what kind of circuit is deciding whether the value is allowed in? You're being too low level. Think back to your register chip, right? What input bit did it have that controlled whether or not you could write it? The load bit, right? So ultimately, these destination bits are going to be wired to the load bits on the destinations. Think about it. All right, so if you can have multiple load bits set to 1, and then you can just change multiple destinations. So we'll take that value and put it both in D and in M. So what does this let us do? It lets us load loop into the address register, and then based on the contents of D, we decide whether we are going to jump. Let me do a save as here. We'll call this ASM2. Oh, I meant to call it ASM2.asm. All right. So now I'm going to load this program into my CPU emulator. Oops, in line 6, destination expected. What? I seem to have a syntax error. How embarrassing. So what does it consider line 6 to be? Oh boy, am I confused. Oh, would it be line 6 of the source? At 5, D equals A at X, M equals T. I wonder if I got this backwards. All right, let me load it again. Aha. These destination flags have to be in a specific ordering. So I think the order is A, M, and then D. I got it mixed up. So if you see an error like that, well, fix it like I fixed it. All right, so now I've got a legit program. So I'm going to walk through it, and we're going to watch it in action. Oh, actually, here's something else fun you can do. You can switch from ASM to binary. You can see it as machine language instructions. Now, let's say you look at the binary and you're like, I want to see a number, but not that. Well, you can look at it in decimal. You look at it in decimal, but you're like, I can't really figure out what the bits are, and all the negative signs are driving me nuts. So now you switch to hex, and now you're like, oh, hex is where it's at. Now, why do I say that? Each hexadecimal digit corresponds to exactly 4 binary digits. So hex often provides a nice way to visualize a binary value in a compact way. of course, most useful is the binary itself. And here you can see exactly what your instructions assembled into at the machine level. Is that going to help us now? Well, no. I'm going to switch back to ASM. But as you're playing around with this, I encourage you to flip between these representations to see what you've actually got. Now, here's something else interesting. Notice that in this representation, sorry, back row, my labels are all gone. It actually replaced them with the numerical values that correspond to them. So at 4 is my loop. My loop wound up being address 4, and it'll jump back to that. So let's march through it and see what it does. I load a 5 into the address register. I set D equal to it. Then I load a 16 into my address register, and I say M equals D. And now location 16 has a 5. Now I load 16 into my address register, and I say MD equals M minus 1. So now both D and M have the value 4. Now I put a 4 in my address register, and I say D semicolon JGT. Look at D, and if it's greater than 0, I jump. Boom, it was greater than 0, I jumped. I have a loop. Whoa, looping. All right, I load 16 to the address register, MD equals M minus 1. D and M are both 3. I check D, is it 0? Yeah, I loop. And I keep going, D and M are both 2. I jump back, D and M are both 1, it's still greater than 0, I loop. Oh, now they're both 0. I check, I don't loop. I have exited. And we now have our first machine language loop. All right, so you got 2 programs to write. Your first assignment for the semester, in which I'm giving you a full week to do it. So it's due on Tuesday. You've got to write 2 programs. One of them is going to multiply 2 numbers. That's all. Just multiply 2 numbers. The other is going to use the screen and the keyboard. And you should certainly read up on those, but I'll be doing examples of screen and keyboard on Thursday. All it really comes down to is, if you're holding down the space bar, it fills the screen black. If you pick up the space bar, it goes white. Those are the 2 programs you're going to write. Yes?
Why HDL doesn't work?
Right, yeah. So the time has come where we're going to need to figure out what's going on. Send me an email, Andre, reminding me to look into it. And I'm going to do a little, and also do some Stack Overflow as well. And in Googling, let's see what we can figure out together to get your code going. Yeah. All right, cool. Any last questions? Yes.
With the multiplying program, are we going to like multiply any numbers, or can hard code them in our program?
So the numbers will be hard coded, but it should work no matter what numbers you hard code. Yeah. So those are given in the chapter 4 folder. They're sketched out for you. I think there's some starting files where you can start entering your code. So I encourage you to go ahead, get started on those between now and Thursday. Come to Thursday with some questions. Yes? No, project 4 will be due. Let's see. So yeah, I'm speaking of project 4. Let me see when I said it was due. What I said it was due on the website is when it's due. Project 4. So this will be due Monday night, basically. So you've got a week to do it. And then Tuesday, a week from today, will be the class where we start talking about how to design a CPU. So yeah, you basically got a full week for this one. All right. Have fun with it. I'll see you Thursday.